Welcome to the video lecture on antiderivatives. We're now going to be moving into a whole new branch of calculus called integral calculus, and it's the inverse of derivative calculus. So we're going to be talking about something today called the antiderivative. Just like its name implies, we're going to be kind of going backwards. This time, instead of being given a function f and asking for its derivative, now we're going to be given the derivative and asking for the original function f. And going backwards can be quite a bit more difficult and more challenging to do, as we will find out. So let's take a look at some examples. Given a function little f, can we find a function capital F such that the derivative of big F is little f? So we want the derivative of big F to be little f. So what they're giving me here, 2x, is a function that is already the derivative of something else. And that's what we're trying to come up with. So what function would have as its derivative 2x? Well, hopefully you can guess that that's going to be x squared, because when we use our derivative rule, we would bring down the 2 and subtract 1 from the power, and that's just going to give me 2x for an answer. Well, how about if I made it x squared plus 1, or x squared minus 5, or x squared plus pi? Would those also have as their derivatives 2x as well? Yes, because the constant is going to go to 0 each time. So the problem with these antiderivatives is there's not going to be a single solution. There's actually going to be a whole family of solutions, and the way that we're going to designate that is we're going to write sort of our general antiderivative, the function part, as x squared, and then we're going to show that you could also tack on any constant on the end and it would still have the correct derivative as well. So what we're going to do is we're going to write a plus c on the side, and that c is going to represent all of those possible constants that you could think of, okay? And it would still satisfy that capital F prime is going to be little f because c would go to 0. So whenever you're finding an antiderivative, your answer is not just going to be the function, it's going to be that function plus a c on the end. So you don't want to forget your plus c's. So let's try to figure out a few more. So let's try to find a function whose derivative would be 3x squared. Well, your first thought should probably be that because we know derivatives, you bring down the power and you subtract 1 from the power, we probably are going to need to have a function that has a power that's 1 higher so that it turns into an x squared. So that means we're probably going to need to start with an x cubed. And then if we double check this, we would bring down the 3 and subtract 1 from the power, and that's going to give us exactly this 3x squared that we want. So this is perfect. X cubed works. Then, to represent all those constants, we're just going to put a plus c on the end. Now, what if I want to come up with 5x cubed? So, using that same thought process, we know that we probably need to have something like an x to the 4th, so that when I bring down the 4, the new power would become a cube. Now that'll give me the right x, but it doesn't give me the right coefficient. I've got two problems. One problem is I want to have a 5, and the other problem is when I take this derivative, the 4 comes down and I don't see a 4 over here at all. So what we're going to do is if we were to bring down that 4, we would want to cancel it out, right? So what we could cancel it out with is a 4 already in the denominator. So now when I bring down the 4's cancel out, giving me a coefficient of 1. Well, that's good, but it isn't a 5. I want a 5. So all we have to do is leave that 5 in there so that when we bring that 4 down, it cancels out and that 5 will stay put and the new power on the x becomes that cube. So this is going to be our new rule. Notice what we did with the x. It was a cube. We added 1 to the power and then we divided by that new power. And that's going to be the essence of our power rule when we do these antiderivatives. And of course, we want a plus c on the end. So now if we look at this next example, 3 sine squared x cosine x. This one is a little bit trickier to do. You have to think a little bit about this before you could probably guess or figure out what it is. The idea behind this and the thing that you want to be thinking about is your chain rule. If you want, you could rewrite this as 3 sine of x quantity squared cosine x, and that might help you see what exactly is going on here. If we had sine of x quantity cubed, then we would bring down the 3, which would take care of that. We would subtract 1 from the power, which would make it a square, so that we would get that. And then the chain rule says we have to multiply all of this by the derivative of what's inside, and the derivative of sine of x is cosine x. So that would take care of that. So this is exactly what we want. We just need a plus c on the side. Okay? So keeping that in mind, let's try this next one right here. X over square root of 1 minus x squared. So let's think about rewriting this. I'm going to take that radical and I'm going to rewrite it as a 1/2 power, but because it's in the denominator, I'm going to make it a negative 1/2 power. Now, if you keep in mind about derivatives and powers, we usually want to have one higher power over here so that when we take its derivative and subtract 1 from the power, we end up with the power over here, just like in this example up here. So starting with that, if we think of this 1 minus x squared, over here it has a negative 1/2. What would be one higher power from that? What would be negative 1/2 plus a 1? Well, that would be a 1/2. So let's see what the derivative of this would give me, and let's see how close we are to getting what we're supposed to be getting over here. So the chain rule says that the derivative of this, you bring down the 1/2, what's inside stays inside, you subtract 1 from the power, and 1/2 minus 1 is negative 1/2. And then we have to multiply this by the derivative of what's inside. The derivative of 1 minus x squared is a negative 2x. So the 1/2 and the 2 actually end up canceling each other out, which is good news because I don't have any constants over here. I have that negative x left over, and then I could take this 1 minus x squared, change it into a radical because I have that 1/2, and flip it down into the bottom because it's negative. So let's compare this answer to what we want it to be. They're very, very close. The only difference is the negative. So how do I clear out a negative? Well, if I throw in a negative in my initial answer over here, then that negative would stay put and would then multiply by this negative that we get from the negative 2x, and these two would end up canceling out, giving me a plus x. So by just throwing in that constant out front, that negative 1 out front, it clears out the negative that we didn't want for our answer. So this is the correct antiderivative to give me back this expression. And all I have to do now is put on that plus c on the end, and we'll have the right answer. Okay? So how is this next one different? Well, the big difference is there's no x on the top. So if we were to move this up and think of this as a negative 1/2 power, the chain rule is really going to give us trouble because when I make any sort of a guess over here, I'm automatically going to get that x showing up when I multiply by the derivative of this inside function. So there's no way around getting rid of that x unless we are really creative and think outside the box. And what you have to realize is that this is actually not going to be any kind of an algebraic answer like we had for the last one because of that missing x. What it actually is something we have learned before that is probably escaped your memory. It's not one of these more common ones that we use quite often. But this is actually a trig function, an inverse trig function. It's arc sine of x, and this is one that we have learned before. The derivative of the inverse of sine of x is 1 over the square root of 1 minus x squared. So that one you wouldn't really be able to guess on your own unless you've seen that derivative rule before. Okay? Put a plus c on the end, and now we have the correct antiderivative. How about secant squared of x? What function has secant squared as its derivative? This is another one of these that you kind of have to have memorized. We know that the derivative of tangent is secant squared. So this antiderivative must be tangent of x with a plus c. Okay, how about cosecant of 5x times cotangent of 5x? What function has cosecant times cotangent as its derivative? That's another one of those trig rules. We know that the derivative of cosecant is negative cosecant cotangent. So let's think about how we could alter that a little bit to make it look like this. We know it's probably some kind of a cosecant. Since I need 5 x's in there, I'm going to need a 5x here. Now the derivative of this should be negative cosecant 5x cotangent 5x, and by the chain rule you also have to take the derivative of this 5x, which would give me a 5. Now I don't have a 5 over here and I don't have a negative over here, so what I could do is divide this by negative 5 so that these cancel out, giving me exactly that cosecant 5x cotangent 5x that I'm trying to get. So by dividing through by the negative and the 5, that fixes my problem. So my answer is going to be cosecant of 5x divided by negative 5 plus a c. Okay? Then on the last example here, this is just a normal polynomial. So to take the derivative of each individual term would be easy to do. We're going to do that same idea but do it with an antiderivative. So we're just going to take the antiderivative of each individual term. So what would I need to have so that when I take its derivative I would end up with an x squared? Well, I need one power higher. If I were to take the derivative of x cubed, that would bring down the 3, and I don't want a 3. So I'm going to need to divide by 3 to get rid of it. So it's this power plus 1 divided by that new power. Now if we go to the middle term, in order to get a minus 3x, I know I'm going to need an x squared. That would bring down a 2, which I don't see over here, so I'm going to need to divide by that 2. And what I do want is that minus 3, so I'm going to leave that minus 3 in my answer so that it will stay put when I bring down the 2. The 2's cancel and I just have the minus 3 left over. And then finally for the 2, what has 2 as its derivative? 2x. And put a plus c on the end, and now each of these will have the correct derivative. So we say that a function capital F is said to be an antiderivative of a function little f on an interval if the derivative of capital F is equal to little f for every x on that interval. So in other words, little f is your original function and the derivative of big F should equal that little f. Now one of the things that we've already noticed is the result of this theorem. So this theorem says that if f is an antiderivative of little f on an interval I, then g is another antiderivative of little f on interval I if and only if g is that big F plus a constant. In other words, you can only have two different antiderivatives of a single function f only if they differ by that plus c. So one of them could be, x plus 1, and then the other one would be x plus 2 or something like that. They're only different by the constant on the end. Now we're going to prove this since this is a calculus course. And in the course of our proof, we're going to make use of this theorem that if the derivative is 0 everywhere on an interval, then the function must be constant on that interval. And we actually have proved that in a previous lecture. Okay, so if the derivative is 0 everywhere, then the function must be constant. Okay, so let's prove one direction. This is actually a two-direction proof because it's if and only if. So we have to show both directions. So the first thing we're going to do is show that if we assume that f and g are both antiderivatives of f, then we want to prove that that implies that g and f just differ by this constant c. In other words, g is just this f plus some constant. So what we're going to do is we're going to define a new function h of x to be big G of x minus big f of x. So we're just creating a new function here. Now what we're going to do is really a proof by contradiction. What I want to show is that h is really just this constant c, but I'm going to prove it by contradiction. So I'm going to assume that h is not a constant and show that there's a contradiction. So let's suppose that h is not constant. Then if you have a function that is not constant on some interval I, then that implies that there has to exist, that's what this backwards e means, there has to exist an a and a b, and let's just assume that a is smaller than b, such that h of a is different than h of b. If you're not constant, then you must have two different y values, at least somewhere on that interval. Okay? Now, since h is continuous, because f and g are, and differentiable, since f and g are, then the mean value theorem applies. Okay, do you guys remember what that says? The mean value theorem says that there has to exist some number c in this interval, a to b, such that the derivative at c is equal to the slope of the secant line between these two endpoints. So that would be h of b minus h of a, the change in the y's, over b minus a, the change in the x's. So the mean value theorem says there has to be a tangent line slope that's equal to the secant line slope somewhere in the interval, as long as you have a continuous and differentiable function. Well, what do we know about h of a and h of b? We know that since h of a doesn't equal h of b, then that means that this numerator can't be 0. If they were equal, then this would be 0, but if they're not equal, then that means h prime of c can't be 0. Okay? Well, what do we know about h prime of c? H prime of c, by definition, how did we define h? H was g minus f. So h prime of c would be g prime of c minus f prime of c. And remember that g and f were both antiderivatives of this little f. So this is going to have to be 0, since they both have the same derivative. They're both little f. They're going to subtract out and be 0. So we have our contradiction. We said over here by the mean value theorem that this derivative couldn't equal 0, but here we just showed that it did equal to 0. So that's our contradiction. And we obviously know that the mean value theorem is true, and we know based on our assumption that the way we've set up our h, this result would be true. So that means our assumption that h was not constant and that h of a was different from h of b, that must have been a false assumption. So therefore, h must be constant. So if h is equal to g of x minus f of x, and we just said that h is some constant, let's call it c, then that means that g of x is f of x plus that constant. So that's what we were trying to prove. Okay? So that's kind of tricky. That's the more difficult direction of the proof. Now let's do the other direction. So this time we're going to assume that g is f plus a constant for every x in our interval, and we just want to prove that capital G is therefore also an antiderivative of f as well. Okay, so if g of x is equal to f of x plus c, and that's our assumption when we're going in this direction. And we already know that big F is an antiderivative of little f. That was also one of our assumptions. So that means the derivative of big F is equal to little f. So these are our two assumptions. Then g prime of x, therefore, would be the derivative of f of x plus c. And the derivative of capital F of x is f prime of x. The derivative of c goes to 0. And the derivative of capital F we know is little f because capital F was an antiderivative. So we just showed that g prime of x is equal to little f of x, which implies that g must be an antiderivative of little f. That's what being an antiderivative means. It means taking your derivative gives you back that little f. Therefore, g must be an antiderivative of little f. So there's our proof, and we got both directions. Okay? All right. Let's talk a little bit about some notation now. So recall that when we talk about derivatives, we have lots of different notations. You can use f prime, you can use y prime, you can use dy dx. I'm going to use that dy dx notation. So suppose that dy dx is equal to this little f of x. Remember when we talked about differentials, we could take that dx and sort of move it to the other side and write this in differential form. So dy is equal to f of x dx. So we're going to use that when we talk about these antiderivatives. Now I'll come back to that in a moment, but let's take a look at what the antiderivative of 3x squared is. What function has as its derivative 3x squared? Well, we know that that's got to be x cubed, because when you bring down the 3 and subtract 1 from the power, you get 3x squared. But we also know from that previous theorem that any constant added to the side of that will also be an antiderivative. So we're going to put in that plus c. So here's the notation that we're going to see. We're going to see that this function that we're looking for is going to have this notation. You'll see this sort of big S shape, and you'll see that function, whatever this is, inside of that S shape with a little dx on the side. And the answer to this is what that capital F of x represents with a plus c on the side. So this means, in words, the antiderivative of f with respect to x. That's what this is telling me, just what variable to use. So if I show you with a specific example, this specific example right here, this is what it would look like. You see this symbol. This is called an indefinite integral. And it is synonymous with antiderivative. So if you see that integral symbol in words, that just means find the antiderivative of whatever function you see inside. And I'm going to write that 3x squared on the inside. And for notation purposes, we're going to have that dx on the side. And that comes from this differential notation over here. I'll explain more about that in a moment. This is called your integrand. And that dx just tells us the variable of integration that we're supposed to be using. So this one is telling me integrate with respect to x. The answer that we get is this answer we got up here, x cubed plus c. So this is called our constant of integration. Now, students often get confused by that dx in there. Why do we have to write that dx in there? What do we do with it? Well, it doesn't do anything at all in terms of calculating your answer. It's purely a notation issue. The integral symbol and the dx symbol, they always go together. They're a pair. You can't have one without the other. And what that dx is doing is it's just telling you what variable to use when you integrate. So I could rewrite this same exact problem, but I could write it this way. The integral of 3y squared dy. And this is now telling me integrate this function with respect to y. So my answer would be, well, what function in terms of y's has as its derivative 3y squared? Well, that would just be y cubed plus c. So it's the exact same problem, but I just switched variables. Another reason why you need to have those in there is when you get to higher levels of calculus, you'll see several integrals nested inside of each other. This is called part of multivariable calculus, where you might see a problem like this, 3x squared yz, and then you might have a dy, then a dx, and then a dz. Triple integral. We're not going to do that in this course, but when you get to multivariable calculus, you might see a problem like this. And this first one means integrate this function just with respect to y, and then you're going to integrate that answer just with respect to x, and then you're going to integrate that answer just with respect to z. So if you have multiple variables involved, that dx or that dy or that dz is really important so that you know which one you're supposed to be working with. So it's purely a notation issue. It's not really going to affect how you get your answer at all. Now there is an inverse relationship between integration and differentiation, because these indefinite integrals are exactly the antiderivative, the opposite of the derivative. So when you see the integral of f of x dx equals capital F of x plus c, that just means that your answer, capital F, is an antiderivative of little f. So its derivative should be this function inside here. So you can always check your answers by taking the derivative of your answer and making sure that it gives you back what you started with inside the integral. Now integrals and derivatives undo each other because they are inverses of each other. So that's what these two statements are going to say. If you take the integral of the derivative of capital F, notice what we get. Well, the derivative of capital F is little f, and the integral of little f is what we're calling capital F. So you get back that capital F. So the integral of the derivative of f is f. In other words, the integral and the derivative, it's like they're canceling each other out, and you're just going to get back what you started with. Okay, this is the same idea but in the other direction. So here, if we start with a derivative of an integral of this function little f, that becomes the derivative of capital F plus c. The c goes to 0, and f prime is little f. So you get back little f again. So again, it's that sort of cancellation idea. The derivative of an integral, they cancel each other out, and you're just going to get back what you started with. So if we started with little f, we're going to get back little f. Okay? So that's that inverse relationship between derivatives and integrals. Now here's some of our formulas that we're going to come up with, and they're based on our differentiation formulas. So if we know that the derivative of a constant is 0, then we know that the integral of 0 must be a constant. Okay, the integral of this right side should give us back the left side. Since we know that the derivative of a constant times x is just the constant k, then the integral of the k must be k times x. Okay, so again, the integral of the right side should give you back the left side. The integral of a constant times a function is the constant times the derivative of that function. So the integral of a constant times a function, you can sort of pull that k out if you like, and you're just going to take the integral of the function part and multiply that answer by k. So this is just like that constant multiplier rule that we have for derivatives. The constant multiplier will stay in your answer, and you just integrate the function. The derivative of a sum or difference is the sum or difference of the derivatives. Same with integrals. The integral of a sum or difference is the sum or difference of the integrals. Now this next rule, we've already sort of explored it, but it's probably going to be one of your most useful rules, that power rule. Now for derivatives, the power rule says bring down the power and then subtract 1 from the power. We're going to do exactly the opposite of that. So if you start with an x to the n, when you integrate it, this time you're going to add 1 to the power and divide by the new power. Okay, so instead of multiplying, we're dividing. So add 1 to the power and then divide by the new power. Now this is not true if your power is negative 1. In other words, if this is 1 over x. That has a totally separate rule, which we'll get to in later lectures. But my hint here would be that that should look something like a logarithm. We know that ln of x has as its derivative 1 over x. So this is actually going to be an ln. But you're not going to be expected to know that yet. But just know that the power rule doesn't apply if this power is a negative 1. Okay, we know that the derivative of sine of x is cosine of x. So the integral of cosine of x is sine of x. The derivative of cosine is minus sine. So the integral of positive sine would need to be a negative cosine. So that when I took the derivative of negative cosine, the cosine becomes a minus sign and the minuses cancel each other out, giving me back this positive sign. So this is a little bit confusing because in our derivative rules, the sine turns into a plus cosine and the cosine turns into a minus sine. Here it's kind of reverse. The integral of cosine is plus sine and the integral of sine is the one with the negative. So it's sort of opposite. We know that the derivative of tangent is secant squared. So the integral of secant squared will be tangent. We know that the derivative of cotangent is minus cosecant squared, so the integral of positive cosecant squared will be minus cotangent of x. We know that the derivative of secant is secant times tangent, so the integral of secant times tangent is secant back again. And finally, the derivative of cosecant is minus cosecant cotangent, so the integral of cosecant cotangent would be negative cosecant x. You need that negative in there to counterbalance the negative that you would get when you take the derivative of this. Now notice for these trig integrals, I told you the integral of cosine and the integral of sine, but I haven't told you in this list the integral of tangent, the integral of cotangent, the integral of secant, or the integral of cosecant. These four are secant squared, cosecant squared, secant tan, and cosecant cotan. Those are special types of expressions in there. I haven't told you what what the integrals are of these other 4 trig functions. And that's because they're more complicated and they're going to involve, again, some of those ln's. So these are a little bit tricky to do yet. We don't know what those are yet. All right, let's try some examples. So integral of 5 dx, this just means what function has 5 as its derivative? Well, we know that that would just have to be 5x. And then you always want a plus c on the end. Okay? How about x squared plus 5x plus 6? What function has an x squared as its derivative? Well, now we're going to use that new power rule. So the new power rule says you add 1 to the power, which is going to make this a cube, and you divide by that new power. And that will check out because when I take the derivative of x cubed, the 3 comes down, canceling out the 3, making it go away, leaving me just that x squared. Then we go to the middle term. What function has 5x as its derivative? Well, the 5 is a constant multiplier, so it's going to stay there. And the integral of x, using that power rule, if this is x to the first, we're going to add 1 to the power, so it becomes a square, and we divide by the new power. And again, if you take the derivative of that, you can double check and see that you get back 5x. And then for the 6, the integral of 6, the 6 stays there and you just get that 6x. And there's a plus c on the end. Okay, for the next one here we have a radical, and just like we would have done for derivatives, you want to change this to its fractional power first so that you can apply that new power rule. So the power rule says add 1 to the power. 1/2 plus 1 would be 3/2, and then we're supposed to divide this by 3/2. Well, that's kind of messy, so what would you do to simplify it? You'd want to multiply this by the reciprocal, which would be 2/3, and that would flip this over and get rid of it. So then this answer becomes 2x to the 3/2 over 3. So here's what I do. And this is only true when you have fractional powers. Instead of dividing by that new power when it's a fraction, that will always be the same as multiplying by the reciprocal. So I just go directly from here to here and I skip this whole step of dividing by the new power. I just flip it over right away and stick it out front. And of course we want a plus c on the end. Let's try that again on this one. So here we have a cube root, which is a 1/3 power, but because it's in the bottom, that means it's negative. So if we use our power rule, we want to add 1 to the power. Negative 1/3 plus 1 is negative 1/3 plus 3/3, or 2/3. And then your reciprocal power will go out front, so you should have a 3/2 out front, and then a plus c on the end. Now for this next one, here we have a quotient. And in derivatives, we learned a quotient rule. The bad news is for integrals, there is no quotient rule or product rule at all. We're not even going to learn one later on. There isn't a rule at all that exists. So the only way to deal with a quotient is to try and rewrite it in a different way so that it turns into something you do know how to integrate. So the trick that I'm going to use here, I'm actually going to show you two options. Option number 1 is you can move this up to the top using parentheses around that numerator and change it to a negative 1/2 and then distribute that across. So this would be x to the first, and then when I distribute x to the first times x to the negative 1/2, you add those powers when you multiply the bases. So x to the first times x to the negative 1/2 is x to the positive 1/2, plus when I distribute the 3, I get 3x to the negative 1/2. So I haven't done any integration yet, I just rewrote it in a different way. But now it's just a power rule, a sum of two power rules. So the integral here would be x. When I add 1 to this power, 1/2 plus 1 becomes 3/2, and you put the reciprocal out front. Plus, when I add 1 to this power, negative 1/2 plus 1 is positive 1/2. The reciprocal would be out front. 2 over 1 is just 2, but I also had that 3. And 3 times 2 is going to give me a 6x to the 1/2 plus that 2/3 x to the 3/2 plus c. So here would be my final answer. Now a second option, I won't do it all out, but another option would be to just divide that square root of x into each of the terms in the numerator, and you're going to get exactly the same expression when you do that. Okay? All right, let's take a look at number 6. So here I see radicals again. We're going to want to change them to their fractional powers. So cube root of x is x to the 1/3. Think of that 3 over 4 as just a 3/4 coefficient, and the square root of x is in the bottom, so when I move it up to the top, it becomes a negative 1/2 power. So now I have again two power rules being added together. So this becomes x. When I add 1 to the power, 1/3 plus 1 is 4/3, and the reciprocal will be 3/4. Plus, that 3/4 is going to stay there, and when I add 1 to the power, negative 1/2 plus 1 is positive 1/2, and the reciprocal will be 2. That 2 will cancel with my 4, giving me 3/2 x to the 1/2 plus 3/4 x to the 4/3, and then of course my plus c on the end. Okay, here were all my answers. Let me put some boxes around them so it's more easier to tell what our final solutions were. All right, let's try the next example here. 1 over 5x quantity squared dx. So the first thing we want to notice here is, again, we have that quotient, so we got to change it so it's no longer a quotient. And I also have that power. So let's just go ahead and square and turn this into 25x squared. And that means we have this 1/25th. You can think of that as your coefficient. And if I move that x up, it just becomes an x to the negative 2. Now that 1/25th, you can either think of pulling that out or just leaving it where it is, because it's not going to go anywhere. It's a constant multiplier. And then when I take x to the negative 2 and I integrate it, I'm adding 1 to the power, so it becomes a negative 1. And this isn't a fraction, so I'm just going to divide by that new power with a plus c on the side. Now to clean all of this up, that 25 and that negative are going to get multiplied together, so that'll be a negative 25, and this x to the negative 1 could flip back down to the bottom, so there's nothing left in the top but a factor of 1. And then we have our plus c on the side. So there's our final answer. Okay? All right, now let's do some trig ones. So the integral of sine x plus 3 cosine x, just do each one individually. What function has as its derivative sine of x? Well, it's going to involve a cosine, but the derivative of cosine is actually minus sine of x. So I need a negative in front to counterbalance that negative that I'm going to get when I take the derivative to double check. So the integral of sine x is actually minus cosine x. Plus, the 3 will stay there. What function has cosine as its derivative? That is just sine of x. The derivative of sine is positive cosine, so I don't need any negatives to balance anything out. Put a plus c on the end, and we have our answer. Now when we see this, again, it's one of these quotients, so you want to try and rewrite it in a different way so that you can use one of your rules, because we don't have a quotient rule. So here's what I think of doing. I see that sine squared on the bottom. So what I'm going to do is I'm going to break it up, and I'm going to put one of the signs under the cosine, and I'm going to put the other sign under just a factor of 1. So this is exactly the same as what I started with. I'm just sort of breaking it apart into pieces. And the reason I'm going to do that is because cosine over sine is cotangent of x, and 1 over sine of x is cosecant of x. If you prefer, you can switch the order around. It doesn't matter which one of these comes first. But this now is exactly one of our rules. What function has as its derivative cosecant times cotangent? Well, that's a cosecant, except the derivative of cosecant is negative cosecant cotangent. So I don't want that negative to show up, so I need a negative out front to cancel it out when I take my derivative. Put a plus c on the end, and now I have my answer. Okay, on this last one here, we've got cosine over 1 minus cosine squared x. So this one, unfortunately, you can't break this up. You're not allowed to do that because the denominator is not a single term. It's actually the difference of 2 terms. So the only way to kind of manipulate this is to try and turn that denominator into a single term. And lucky for us, this is one of those identities. This is that Pythagorean identity. We know that sine squared plus cosine squared equals 1. So 1 minus cosine squared is just sine squared of x. And this is now exactly that integral, which we already know the answer to is negative cosecant x plus c. So you might have to use some identities on some of these trig integrals to make them work out for you. So be on the lookout for that. Okay, now what we're going to talk about is something called a differential equation. A differential equation in x and y is just an equation that involves x, y, and derivatives of y. So here's a couple of examples. Y prime equals to 3x, or dy dx equals x squared plus 1. If you wanted a more complicated one, you might see something like y double prime plus 2y prime equals 3x minus y. And these are all differential equations because they use x's, they use y's, and they use derivatives of y's. Now these aren't your typical equation. Normally when we solve equations in algebra, we're getting a number for an answer, like x equals 5. This time, we're not going to get a number for an answer, we're going to get a function for an answer. Think about this one right here for a moment. This is saying what function y would have as its derivative 3x. Well, we know from our rules that that's got to be 3x squared over 2 plus a c. If you were to take the derivative of that function, you would get back 3x. And we're not getting, just x equals 5 for an answer. We're actually getting a formula for an answer. And we're not just getting a single formula, we're actually getting a family of answers because of that plus c. And all of these graphs, if you were to graph these would just look like parabolas, and the plus c acts as a vertical shift to shift them up or down. So there's a whole family of curves that would satisfy this differential equation. So to solve a differential equation means finding a solution or a family of functions which satisfies that equation. So we have two types of solutions. A general solution is when you're trying to find the family of solutions, and that's going to be when you find that general antiderivative and then you take a plus c on the side. So that would be this right here. This is called your general solution. A particular solution finds the specific solution, the specific curve to the differential equation that passes through something called an initial condition. And an initial condition is just a point, an x and a y. So there's only going to be one curve that passes through a certain ordered pair, like 0, 0. So when you're finding a particular solution, you're finding which one of these curves goes through that particular point. So the initial condition is just a point that one of the curves passes through that you want to go through. So for example, y prime equals 3x squared, and we want to find the solution to that with an initial condition of 0, 0. So think about it. What function, y, has as its derivative 3x squared? Well, what function has as its derivative 3x squared? That's got to be an x cubed plus possibly a constant on the end. This is called your general solution. Now, if c was 0, then this would just be y equals x cubed, which would just be a normal cubic function like this. So that would be c is 0. If c was 1, then that would just be this same x cubed graph, but shifted up 1 unit. So its graph might look something like this. If c was 2, then you would shift it up 2 units. If c was 3, then you would shift it up 3 units. If c was negative 1, you would shift it down 1. So you kind of get the idea. You get basically a graph that is a bunch of parallel graphs. These graphs are never going to intersect each other. They're just vertical shifts of each other. The whole collection of them is called your general solution. These are a family of curves. Now, we want to find the particular one that goes through 0, 0, and there's only going to be one of them that does, since these never intersect. So 0, 0 is right at the origin. So that means we're looking at this curve right here. And if you wanted to physically find that c, if you couldn't just tell from our graph, here we could, what you could do is you could let 0, 0 be your initial condition. So you're going to let x be 0 and y be 0, and you're just going to plug them in to that general solution. So if I let y be 0 and x be 0, then that tells me that c must be 0. So this would be called my particular solution, and its particular equation would just be y equals x cubed, and the c is 0, so there would be no plus c on the end. And that's this particular graph right here. Okay? So what we're going to do is practice finding the general and the particular solutions to some differential equations. So suppose we have the the differential equation dy dx equals 2 times x minus 1 in parentheses, and f of 3 is equal to 2. So if we wanted to find the general solution, that just means solving this differential equation. So let me show you some notation. First thing I'm going to do is I'm going to split up this dy dx, and I'm going to move that dx over to the other side. And now to undo this derivative and find its solution, that's what an indefinite integral does. It finds an antiderivative. So we're going to take the integral of both sides. Now there's an implied 1 right here. So what function has 1 as its derivative, but we want to use the variable y in our answer? So what function has 1 as its derivative using y's? That would just be y. The derivative of y is 1. So that's your left side. On the right side, we can do a little bit of work here. We can distribute that 2 across, and then we're just going to integrate each of these two terms. So what function has 2x as its derivative? Well, that's just x squared. And what function has 2 as its derivative? That's just 2x. And then we have a plus c on the end. So this is called your general solution, when you have that plus c on the end and you get that whole family of curves. Now what we want to do is find a particular solution. So that's what this is. This is your initial condition, and it really just is a point, because this is your input x and this is your output y. So f of 3 equaling 2 really means the point 3, 2. So to get our particular solution, we're just going to use 3, 2, and we're going to plug in 3 for x and 2 for y into this equation. So 2 goes on this side, 3 squared minus 2 times 3 plus c, and we just solve this for c. So we get 2 equals 9 minus 6, which is 3, and so c is going to be negative 1. So our equation now becomes x squared minus 2x. I'm going back to this general solution, but now I know what my c is. I want c to be negative 1, so I'm just going to put a minus 1 on the side, and this is called our particular solution. Graphically, all of these general solutions, these plus c's, would be all of these different parabolas. We wanted the one that went through 3, 2, which on this graph is this point right here. So that means the only curve that passes through that red dot must be this one in the middle with all those little polka dots, and I'm drawing it or tracing it in red. So this equation right here is that curve that we're looking for. Okay, let's try it again. This time y prime equals negative 1 over x squared, and we want to do this at the point 1, 3. So notation wise, the first thing I'm going to do is change that y prime to a dy dx. I'm going to use that version of the notation for a derivative, and then I'm going to split up that dy and that dx, and I'm going to move the dx over to the other side, and in order to solve for y, I'm going to undo this derivative by taking an integral, an antiderivative. Again, this is implied to be a 1, so the integral of dy will always be just y. On the right side, I'm going to need to rewrite this quotient as a single term. So let's move that x squared up to the top so it becomes negative. And then using my power rule, the negative out front stays there. When I add 1 to the power, negative 2 plus 1 is negative 1, and then I'm supposed to divide by the new power with a plus c. These minuses cancel out, and x to the negative 1 is the same as 1 over x. So this is my general solution. So now to find my particular solution, I'm going to use 1 comma 3 in this general solution. So x is 1 and y is 3. So 3 goes on the left side, 1 goes on the right side. You're going to get 3 equals 1 plus c, so c is 2. So y equals 1 over x plus 2 is my particular solution. And graphically, remember we were trying to go through the point 1 comma 3, which would be right about here. And that's this curve on this side, and it has another copy of itself over here. And the equation that we got was 1 over x plus 2. So that's the normal 1 over x graph shifted up 2 units. So that's why there should be a nice horizontal asymptote at a height of 2 because of that shift up 2 units. Okay? All right, our next example, same idea, but this time we're adding a little bit of a complication. Now I'm not telling you f prime of x, I'm telling you f double prime of x, but I still want to know what f is. So if you have f double prime of x, if you integrate once, that's just going to step you backwards once back towards that first derivative. Then we're going to have to integrate a second time to step me backwards again back to that original function f. So when you're given a second derivative, you're actually going to have to do 2 indefinite integrals, find 2 antiderivatives. And also, to complicate matters, each time you integrate, you're also getting a plus c. So that is why they're telling me 2 different initial conditions here and here. 1 each for each of those plus c's that we're going to end up with. So let's start. Now on this one, because it's using that f double prime notation, I'm just going to show you another option here for how to write this. I am going to put dx's on both sides and then my integral symbol in front. Remember, an integral must always be paired with a dx or a dy or whatever. They just need to be there for proper notation, but that dx doesn't really do much in terms of helping you calculate the answer. Now what function, when you take the derivative of it, gives you f double prime? Well, that would be f prime, since the derivative of f prime is f double prime. Okay, so that left side is just f prime of x. Now when I take the derivative of x, the integral of x squared, or the antiderivative of x squared, that just becomes x cubed over 3. You add 1 to the power and you divide by the new power plus a c. So here's where we get that first plus c. Notice that this is a formula for the derivative of f, so I want to use the initial condition that refers to the derivative of f. So I want to be using f prime of 0 equals to 6. The 0 is my x, the 6 is my f prime. So we're going to put 6 on the left side and 0 on the right side. So this will all go to 0. And c will just be 6. So that means f prime of x is x cubed over 3 plus our c, which was 6. Okay? Now we're not done because we don't want f prime, we want f. And I need to get f prime first so that I can figure out f. So to find f, we have to do that whole process again. So this time I'm going to take f prime of x, stick a dx next to it and an integral symbol, And then on the other side, I'm going to take x cubed over 3 plus 6 and stick a dx next to it and take an integral of that. Now what function, when you take the derivative of it, gives you f prime? That's just f. The derivative of f is f prime. On the right side, what function has as its derivative x cubed over 3? Well, that 3 is like a 1/3 out front. So when you use your power rule, you're going to add 1 to the cube, so that would become a 4th, and divide by the new power. And when you combine those, 1/3 times x to the 4th over 4, that's just going to be x to the 4th over 12. Then we go to the 6. What function has 6 as its derivative? Just 6x. And then we need that plus c on the side. So here is f of x. Now we want to use our second initial condition to find the last plus c. So we are told that f of 0 is 3. So I'm going to use 0 for x and 3 for y, or f of x. So the 3 goes on the left side and 0 goes in for x. So all of these go to 0, so c is just 3, which means my function f will be x to the 4th over 12 plus 6x plus 3. Okay? All right, our next example is a word problem. So this one says the rate of growth dp dt of a population of bacteria is proportional to the square root of t, where p is the population size and t is the time in days. T ranges between 0 and 10. The initial size of the population is 500. After 1 day, the population has grown to 600. Estimate the population after 7 days. Okay, so what we want to know about is the size of the population after 7 days, and 7 is a time. So if we have a time, we should be able to just plug in that t value and find our population. Unfortunately, they don't tell me in this problem directly what that population function is. What they do tell me is something about its derivative. They tell me that its rate of growth, in other words, this derivative dp dt, is proportional to the square root of t. Now, is proportional to, that's called a direct variation. You might have learned about that in intermediate algebra. If something is in direct variation or proportional to something, that means it's a constant times it. So whatever is mentioned here first equals a constant k times whatever is mentioned second. So when it says that this dp dt is proportional to the square root of t, that means dp dt is a constant k times the square root of t. So that's the differential equation that we have to work with. Now we also are told some conditions. We're told that the initial size of the population is 500. So initially, at time 0, the population will equal 500. After 1 day, the population has grown to 600. So the population at time 1 is 600. And we're trying to find the population after 7 days. So we're looking for p of 7. So if I knew my p function, I could just plug in 7 and be done. We don't know p yet, but this differential equation should enable us to figure it out. So that's how we're going to proceed. So first thing I'm going to do is I'm going to break this up and move that dt over to the other side. And then I'm going to stick integrals in front of both sides. So the integral of dp will just be p. Use whatever variable is referred to there. So p has a derivative of 1, so the integral of 1 will just be p. On the other side, I'm going to change that square root to a 1/2 power, so I can use my power rule. The k will just stay there, and I will have 1/2 added by 1. 1/2 plus 1 is 3/2, and the reciprocal, which is 2/3, goes out front. And then there's going to be a plus c on the side. Now right away there's a problem because what we wanted to do was just be able to plug in 7 for t and get an answer. But if you plug in 7, there's too many variables going on here to be able to solve. We need to figure out what k is, we need to figure out what c is in order to plug in just 7 for t. And that's what these two initial conditions up here are going to tell us. So let's use the top one first. P of 0 equals 500. So this is your t, this is your population p. So I'm going to plug in 500 for p and 0 for the t. So that makes all of this go to 0, so c is just 500, which means this population function becomes 2/3 k t to the 3/2 plus 500. Now we're going to use the second initial condition, P of 1 equals 600. And hopefully this will enable us to find out what that k is. T is going to be 1, and our population P is going to be 600. So 600 goes on the left. I get 2/3 k. T is 1. 1 to the 3/2 is just 1, so this will be 600 equals 2/3 k plus 500. So now I can solve that for k. So what I want to do to solve for k first is subtract the 500 to the other side. That'll give me 100. And then to solve for k, we can just multiply by a reciprocal. So let's multiply both sides by 3/2. So this will just give me k on the right. 2 goes into 100 50 times. 50 times 3 is 150. So this formula becomes P equals 2/3 times k, which we now know is 150, t to the 3/2 plus 500. Reducing that, 3 goes into 150 50 times. 50 times 2 is 100. So this is 100 t to the 3/2 plus 500. So now, finally, we just have a function in terms of p's and t's, so we can finally answer this question here. All I have to do now is plug in 7, and that'll tell me what my population p is. So p of 7 will be 100 times 7 to the 3/2 plus 500. And that's not going to be a nice answer, so just use your calculator. Since we're talking about a population, I'm just going to round this off to the nearest whole number, and this is about 2,352, and we're talking about our bacteria population. So that's how many we have in our population after 7 days. Okay? All right, our next example is going to refer to some stuff we've talked about many times before. Positions, velocities, and accelerations. So let's remember the relationship between these three things. Position is kind of your first function, and it measures either your position or your height or your displacement. One derivative of position, in other words s prime of t, is velocity. One derivative of velocity or two derivatives of position is acceleration. So we're going to be using those facts throughout several problems. So here's what we have. A ball is thrown vertically upward with an initial velocity of 40 feet per second from a point 20 feet above the ground. So let me draw a picture of that. We're on this cliff or building or wherever that's 20 feet high, and we're throwing this object up into the air, and eventually gravity is going to pull it back down to the ground. Now, right off the bat, it's telling you several things. It's telling you some initial conditions. It tells you that the initial velocity is 40 feet per second. So our velocity at time 0, right when we throw this into the air, is 40 feet per second. And then it's telling me also that I'm throwing it 20 feet above ground. So my initial height, or my initial position at time 0, is 20 feet. Okay, so that's my initial displacement. Now what do we know about its acceleration? we're assuming here that we're being acted on by acceleration due to gravity, and that's what's going to pull this object back down to the ground. So if you're using units of feet and seconds, what is the acceleration due to gravity? Well, it's constant. It's always negative 32 feet per second squared. That's going to be a given. You can assume that if you're on Earth, acceleration due to gravity is always negative 32 feet per second squared or negative 9.8 meters per second squared. So this is a constant function. So what we want to know with all this information is how long will it take to reach its greatest height. So we want to know when it's going to reach that peak. What is that greatest height? How long will it take to reach the point of release on its way down? How long will it take to reach the ground? And what will the velocity be when it reaches the ground? So it's asking a lot of questions about heights, which are positions, and velocities. So if all we know is that acceleration is constant, how do we go backwards from acceleration to get velocity? We integrate. And then we can go backwards again from velocity and integrate again to get position. So that's what we're going to do. So the key to this is the fact that the acceleration is a constant function. It's always negative 32. It's independent of t. So I'm going to put some dt's on both sides, and I'm going to integrate both sides. What function has as its derivative the acceleration function? Well, that's velocity. One derivative of velocity gives you acceleration. So this left side will be velocity. What's the integral of negative 32? Well, the negative 32 stays there, and you just stick a t on the end. Our variable here is t, not x. So the derivative of negative 32t gives us negative 32, but we get a plus c every time we integrate. So now we want to use our initial condition, and we want to use the one that refers to velocity. So v of 0 equals 40 means I'm going to let t be 0, and I'm going to let my velocity be 40. So 40 goes on the left side. T is 0, which means this whole term goes to 0. So c is 40. So my velocity function will be v of t equals negative 32t plus that c, which we just found out was 40. So we knew acceleration due to gravity, and we just figured out velocity. So now how do we find position? We integrate again. So I'm going to take v of t, I'm going to stick a dt next to it and an integral, and I'm going to take negative 32t plus 40, stick a dt next to it and integrate it. What function has as its derivative velocity? Well, that's position. So the integral of v of t is s of t. On the other side, the negative 32 will stay there, and the integral of t becomes t squared over 2. The integral of 40 becomes 40t, and there's a plus c on the end. So this becomes s of t equals negative 16t squared plus 40t plus c. Now to get rid of that c, we use our initial condition that the initial height was 20 feet. So I am going to use s of 0 equals 20, t is the 0, and s is the 20. So 20 goes on the left, and then all of these t's become zeros. So this is gone, so c is just 20, which means my position function will be s of t equals negative 16t squared plus 40t plus 20. All right, now we have all of the important functions that we need in order to answer all of these questions. So the first question, how long will it take to reach its greatest height? Now we've done this before. You know that if you're going to reach this height up here, that's right where that maximum is. And the tangent line is horizontal there, which means the slope is derivative. or the slope is 0, or the derivative is 0. And what is the derivative of this position? Derivative of position is velocity. So you're going to be at your max when the velocity is 0. So to find the max height, what we're going to do is we're going to set our velocity function equal to 0. And our velocity function was negative 32t plus 40. So when I set that to 0, divide by 32 and reduce that fraction, I get 5/4. And this would be seconds. So it takes me 5/4 or 1 1/4 seconds to reach that peak. Okay, so that's the first question. Second question, what is its greatest height? So how high did we actually get? Well, it's asking about a height, and height is position. So what we want to use next here is the position function, and we want to use it at this particular t value, since that's the time that we're interested in. So we're going to use our position function, and we're going to plug in 5/4 into it for t. So negative 16, 5/4 squared, plus 40 times 5/4 plus 20. And you can just plug that into your calculator, and it turns out to be 45, and our units here for positions would be feet. So that is our maximum height. Okay, the next question says, how long will it take to reach the point of release on its way down? Now, the point of release initially was when we threw that ball up into the air. That's the point of release on the way up, because the ball goes up initially. But then it's going to reach that same height but coming down. So this is what we're looking for, the time it takes to get to that point. Now there's several ways to do this, but the easiest way, I think, is just to use some symmetry. You know that this is a nice parabolic function, a nice quadratic function. We know that it takes us 5/4 or 1 1/4 seconds to reach that max. So it's got to take us another 5/4 or 1 1/4 seconds to reach the symmetric point on the other side. So this time right here has to be 5/4 plus 5/4, or 2 times 5/4, which is 5/2, or 2.5 seconds. So it's going to take me 2.5 seconds to reach the point of release going down. Okay, so that was the next question. Now we move on to the one after that, which says, how long will it take to reach the ground? So now we want to know, when is this going to hit the ground? And what do you know about your position if you're on the ground? You know that your position is 0. So we want to use the position function, the height function, and we want to set it to 0. So we're going to be on the ground when position is 0. So I'm just going to plug in 0 on the left side of my position function, and I'm just going to solve this. Now unfortunately this is quadratic and it doesn't factor, so you would have to use the quadratic formula, minus b plus or minus square root of b squared minus 4ac all over 2a. I'm going to leave that for you to do. And the two times that you end up getting are negative 0.427 and positive 2.927. Obviously we don't want negative time, so the answer that we're looking for here would be 2.927 seconds. So that's going to be when it hits the ground. Okay? All right, the last question here is, with what velocity will it reach the ground? So how fast is it going when it slams into the ground down here? That's asking about a velocity. So we want to use our velocity function, and we want to find that velocity at this time, because that's the time when it's on the ground. So for the last question, we're just plugging in 2.927 into that velocity function. And again, just punch that into your calculator and you get about negative 53.67. This is a velocity, so its units will be feet per second. And notice that it is negative. Velocity does have direction associated with it, and the fact that we're going down into the ground is why this velocity is negative. Okay, next example. A rocket is lifted off the ground with a constant acceleration of 22 meters per second squared. Find the velocity of the rocket and its height above the ground 30 seconds after liftoff. So we have this rocket that's shooting up into outer space with a constant acceleration of 22 meters per second squared. So this is similar to the last example, except that instead of being acted on by acceleration due to gravity and having a constant acceleration of negative 32 feet per second squared, this time this rocket has a constant acceleration of 22 meters per second squared. So if I want to know about velocity, I'm going to have to integrate this once to get velocity. If I want to know about height, which is also called position, then I'm going to need to integrate a second time. So let's go ahead and start doing that. If I put some dt's on the side and some integrals in front, what function has as its derivative acceleration? That would be velocity. And the integral of 22 is just 22t plus c. Now to find that c, we're going to need some initial conditions. So remember, the rocket is starting on the ground and it's just blasting off. It doesn't tell me anywhere in this problem that it has an initial velocity, just that it has a constant acceleration. So my initial velocity, we have to assume, is 0. The initial position, because we're launching off of the ground, would also be 0. So those are my two initial conditions. So if I use this one, I'm going to be plugging in 0 for velocity and 0 for t, so my c is 0. So my velocity function will just be 22t. Now to find height, we're going to need to integrate one more time. So I'm going to stick my dt's on there again. And integrate both sides. What function has as its derivative velocity? Well, that would be position. And the integral of 22t would be 22t squared over 2 plus c, which reduces to 11t squared plus c. And if I use my initial condition that the initial height was 0 because we were starting off the ground, then this is going to be 0 for position and 0 for time. So again, that c is going to be 0. So my position or height is s of t equals 11t squared. So now we can answer our question. It says, find this velocity and height when the rocket is above the ground 30 seconds after liftoff. So find this velocity and height after 30 seconds. So all we need to do is plug in that 30 seconds for our time. So the velocity at 30 seconds will just be 22 times 30, which is 660. And the units here, remember our units for our acceleration were meters per second squared, so velocity should be meters per second. And then to find our position or our height, we're just going to plug in that 30 seconds again. So 11 times 30 squared will be 9,900, and for position or height, our units would just be meters. Okay, the next example. This one says that if the brakes of a car can give the car a constant negative acceleration of 8 meters per second squared, what is the greatest speed it may be going if it is necessary to be able to stop the car within 25 meters after the brake is applied? Okay, so right off the bat, it says that the car has a constant negative acceleration of 8 meters per second squared. So that's our acceleration function. Our acceleration function is a negative 8 meters per second squared. We're going to integrate that once to get velocity, and then we can integrate that twice to get position. Now each time we do that, we're going to get some plus c's, so we're going to need some conditions. So what do we know? Well, we have this car that's sort of starting right here, and it's going with our negative acceleration, and we want it to be able to stop after 25 meters. So if we start counting from here, our initial position from here at time 0 is 0. I'm going to think of this starting point where I start measuring from as my initial position. So at time 0, I'm right at that starting point. So one initial condition would be S of 0 equals 0. The other initial condition that we sort of know is that we are looking for actually the speed or the velocity that we're going right at that point in time. How fast, what is the greatest speed that we can be going right then so that we stop when we travel 25 meters. So the velocity at time 0, that's actually what we're trying to find. We want to know how fast the car is going right when we start. But what we want to know is what will that speed be when the car stops at 25 meters. So we want to stop at 25 meters. Now what do you know if you're stopped? You know that your velocity is going to be 0. So we need the velocity to be 0 after I have traveled a position or a distance of 25 meters. So this isn't really quite an initial condition because the initial condition for velocity is actually what we're trying to figure out. So this one's a little bit more complicated. So let's kind of start and see where we go. We have acceleration. So let's stick our dt's on both sides and integrate both sides. What function has as its derivative acceleration? That would be velocity. What function has -8 as its derivative? That would be -8t plus c. Now I don't know what my initial condition is for velocity, so we can't really figure out that plus c yet. So let's just leave it as a c temporarily, and let's go ahead and integrate again because I do know something about position here. I do know an initial condition for position. So let's stick our dt's on both sides. I'm going to leave that c in there so it'll look a little bit strange. What function has as its derivative velocity? That would be position. What function has as its derivative -8t? Well, that would be -8, and then the t becomes t squared over 2. And then what would be the integral of c? Well, since c is a constant, it would just be ct, because the derivative of ct goes to c. But we get another constant on the end. I'll call that c sub 1. Okay? Now, I've got a couple of c's here, and let me go ahead and reduce my -8 divided by 2. But I can eliminate one of these c's because I knew that initial condition. I'm measuring the car from this starting point. So initially its distance from that starting point at time 0 is 0. So I'm going to use S of 0 equals to 0. So this is my S and this is my T. So if I plug in 0 here and 0 for T, then this goes to 0, this goes to 0, and that means that c sub 1 will be 0. So that's good news because that eliminates at least one of my c's. So my position function is -4t squared plus ct, and then this just goes away. So there's my position function, and this was my velocity function. So what do we want to know now? We want to know, or what we want to happen is we want the car to stop. And if your car is stopped, that means your velocity, your speed is 0. So we want the velocity to be 0 after we have traveled 25 meters. And what's 25 meters? 25 meters is a distance. So this is kind of sort of like a system of equations. We have two different things that we want to be true. We want our velocity function to be 0. Well, here's our velocity function up here. So I am going to put 0 on the left-hand side. And at the same time, I want this position function to be 25. So I'm going to put 25 on the left-hand side of that position function. So this is a system of equations because it has two variables and it's got two equations. So we should be able to solve for both the t and the c. So what I'm going to do to solve this is I'm going to just use substitution. I'm going to solve this for c by adding that 8t over to the other side. And now if I take that c and I substitute it in right here, then I get 8t times t, which is 8t squared, and we're adding to that a negative 4t squared. So combining like terms, that's a positive 4t squared. If I divide both sides by 4, I get 25 fourths. And if I take a square root of both sides, I'm only going to use the positive square root because we're talking about time. This would be 5 halves. So the time it's going to take this car to stop is 2.5 seconds, 5 halves of a second. Is that what the question wanted? No, it wanted to know the speed that I was starting with, which is what we called our c up here. That was this initial velocity. So what we need to know is not t, but c. So since I know t, go back over here and plug it in, and that'll tell you what that c needs to be. And 2 goes into 8 4 times. 4 times 5 is 20. So c is this initial velocity. When time is 0, this goes to 0, and that'll just be your c. So this c represents how fast we were going right from the start. So this 20 is what our answer is that they're looking for. So the greatest speed that I can be going is 20, and my units here were meters per second. So I can be going as fast as 20 meters per second in order to stop in a distance of 25 meters. Okay, so that one was pretty tricky. All right, last example. A direction field consists of line segments with slopes given by a differential equation. These lines give a visual perspective of the directions of the solutions of the differential equation. Sometimes these are called slope fields. So each of these little dashed lines represents a slope. So if you see kind of a flat horizontal line, that means at that point the differential equation is supposed to have a 0 slope. So the graph shown below is the direction or slope field for this particular differential equation. dy dx equals x squared minus 1. So for example, when x is 1, 1 squared minus 1 would be 0. So the derivative is supposed to be 0 at 1. So when you go to 1, that's why these are all 0 sloped lines, nice horizontal lines. So these little dashed lines represent what the slope of the graph is supposed to be. Now remember what a slope does. It tells you the direction that your curve is supposed to go in. So these slope fields or direction fields sort of show us what these solutions should look like. They can, if you kind of follow the dashes carefully, you can almost sketch in what those graphs should look like. And that's what we want to do here. We want to sketch two approximate solutions, including the one that passes through the point -1, 3. So -1, 3 would be right here. So we want to draw the solution that's going to pass through that point and follow the direction of these little dashed lines, because these are the slopes that my graphs are supposed to have. So if we are sort of flat right here, and as we go left, we're following these little dashed lines, you can kind of see that I'm going to have to go down like this, And then as I go right, the dashed lines are telling me to go down, down, and then I level off where that horizontal was, and then I have to come back up again. And following these diagonal lines, you can see there would be the solution through the point -1, 3. Now if I had picked a different starting point, like over here at 0, I would get a very similar shape. It's just shifted down. So I follow these little dashed lines, and you can see the graph looks like that. So these are my family of curves that we've already seen before. These are all those general solutions that are just vertical shifts of each other up and down by that plus c. So what we want to do is use integration to actually find the equation of these different solutions. So we use our differential equation, which is dy over dx equals x squared minus 1, and the initial condition that we're using is that point -1, 3. So if we push that x squared minus 1 over with the dx next to it and integrate both sides, the integral of dy is just y. The integral of x squared becomes x cubed over 3. The integral of 1 is just an x, and we get a plus c. So we're going to let x be -1, and we're going to let y be 3. So 3 over here, -1 cubed over 3 minus -1 plus c. So -1 cubed stays negative. A minus minus becomes plus. 1 minus 1/3 is 2/3. And 3 minus 2/3, that would be 9/3 minus 2/3 is 7/3. So rewriting this equation with that c plugged in, this would be x cubed over 3 minus x plus 7/3. So that should be the equation of this graph right here. Okay? So that's our equation. Okay, so these are called slope fields or direction fields, and they just show these little tiny dashed lines which represent these slopes at various x values, and using those little dashed lines and sort of following them along helps you sketch in what the actual curves and solutions should look like. All right, that concludes our lecture on antiderivatives. Good luck.